Good afternoon, everybody, or whatever time it is for you right now. My name is Hendrik Bayer, and my talk today is about a paper I wrote with Michael Kaisers on novelty and Monte Carlo tree search. So first off, let's start with a bit of motivation and related work. Why do we think Monte Carlo tree search needs novelty? Monte Carlo tree search, or MCTS for short, is the name for a by now pretty large family of sample-based search algorithms that have had tremendous success over the last 15 years. For example, in the field of general game playing, in the field of general video game playing, and of course in recent years as an integral part of several major AI breakthroughs coming out of DeepMind. MCTS is now a central pillar of both learning and planning in the reinforcement learning community, which is why improving it is so interesting to us. Now on to the concept of novelty. In evolutionary computation, for example, it has been found that traditional fitness functions can be deceptive and lead into dead ends. It has turned out to be surprisingly effective in many cases to completely ignore progress towards the actual objective of the search and look only for novel behaviors instead. In classical AI planning, various novelty measures have been used, often within iterative breadth first or best first search, sometimes searching for novelty alone and sometimes for novelty combined with reward, or with heuristic estimates of expected reward. One of our novelty measures that I'll explain later is inspired by such work. And finally, in deep reinforcement learning, novelty has been studied as a form of intrinsic motivation for the learning agent. Reinforcement learning novelty techniques for large problems are often based on so-called pseudo-counts, a generalization of state visit counts for very large state spaces. And this is another idea we'll pick up later. So now that we are sufficiently motivated, in the next part of my talk, I'm going to briefly outline the three concrete definitions of novelty we're using in our ongoing work. So let's say we encounter this tiny toy game state during search and want to measure its novelty, and so our uncertainty of it, or its promise for exploration. We've never seen this exact same state before, as with most states encountered during search, so a simple visit counter would just return 0. What we want is a way to generalize uncertainty, also to such unseen states, to distinguish between more and less novel states. Our first novelty definition, evaluation novelty, does this by making use of a heuristic state evaluation function. Now, as we can see, the state consists of 4 atomic features, which tell us what's on the 4 squares of the tiny board. In this case, there's a red piece on A1, another red piece on A2, nothing on B1, and a blue piece on B2. Evaluation novelty now first looks up, for each one of these 4 elements or facts our state consists of, the highest state evaluation we've ever seen before for any state sharing the same fact. We could, for example, assume that the highest state evaluation we've seen before for any state with a red piece on A1 was 0.4. The highest value of any previous state with red on A2 was 0.3, etc. Now we can determine our heuristic evaluation of the newly encountered state itself, called V of S, and we can compare it to the highest previous evaluations for all facts. If for any fact the new state beats the previously best one, we call the entire state novel. But if all facts of this state have been seen in higher valued states before, we call it not novel. Novel states then get a novelty value of alpha from us, which is marked in red here because it's a tunable parameter of the algorithm, and non-novel states get the novelty value of 0. In our toy example, the highest evaluation previously seen for red on A2 was 0.3. If this new state now is evaluated as 0.4, for example, that beats 0.3 and makes our toy game position novel. This is our first novelty measure. Now, evaluation novelty can only distinguish between novel and not novel. Maybe it would be better to have a finer grained novelty measure, and that's exactly what pseudo-counts can provide. Pseudo-count novelty does not rely on heuristic value estimates, but is based on an estimate for the probability of observing a given state. And that probability is simply modeled as the product of the frequencies of all facts that the state consists of. Imagine, for example, that we've observed 200 other game positions so far, and 41 of them had red on A1, 7 had red on A2, 152 had no piece on B1, and 102 had blue on B2. Then, according to this simple model, the probability of observing this state before we've observed it just now was just 41 divided by 200 times 7 divided by 200, etc., which comes out to about 0.278%. After observing this state, we've now seen 201 states, and we've also seen each fact in it one additional time. So the updated probability of this state is now 0.324%, a bit higher than before because we've corrected our frequency estimates for all 4 facts slightly upwards. The pseudocount for this state is now computed from these old and new probabilities for observing the state, according to this formula, which is taken from a 2017 paper by Jared Martin et al., and which gets us a pseudocount of about 6 in this particular example. And the novelty value of this state is then simply alpha, again a tunable algorithm parameter, divided by the square root of the pseudocount. With this approach, the less the observation of a state changes our probability estimate of seeing it again, so the less an observation surprises us in a sense, the higher the pseudocount will be, resulting in a lower novelty. This is our second novelty measure. The remaining third novelty measure is actually just a slight modification of the second, using a different feature set to compute state probabilities from. Instead of using the atomic facts our states consist of, such as in this case the content of the 4 board squares, this technique instead assumes a heuristic state evaluation function again, for example such a linear combination of feature values, as you can see on this slide, and simply uses the same features that the evaluation uses, extracted from the state with the function phi in this equation. For example, the evaluation function for this game could be using 2 features, the number of red pieces on the board and the number of blue pieces. Then we could again assume these 2 features to be independent, estimate their frequencies from observed data, get the probability of the state by multiplying them, and so on, just as before. And this is finally our third novelty measure. And that brings us to the third part of my talk, in which I'm now going to explain how exactly we're using these 3 different definitions of novelty in order to enhance Monte Carlo tree search. And here's how that works. Every MCTS simulation, when adding a new leaf state S to the search tree, now produces not only a state evaluation V of S, for example with an evaluation function, but also a novelty value N of S, with the novelty measure of our choice. And when we're backpropagating simulation results to the visited nodes, we're backpropagating both values. Every tree node still maintains a sample counter N and a value estimate V bar for each action A, as the average overall evaluations in the subtree that action leads to, here in blue. But in addition, now also a novelty estimate N bar for each action A, as the average overall novelty values in the subtree that action leads to, here in green. This slide shows how these 2 estimates are incrementally updated. And this slide shows how that lets us improve our tree policy. Whenever we need to pick an action at a given tree node during an MCTS simulation, vanilla MCTS would pick the action that maximizes a formula similar to this one, a formula that combines the current value estimate for the action in blue with an uncertainty bound for that estimate, here the square root term, and trades them off with a tuned exploration parameter k. Our proposed novelty-enhanced MCTS now replaces this formula with one that uses a linear combination between value in blue and novelty in green. Maximizing over this formula now means that the search takes the average novelty value into account, which is basically the expected novelty when visiting any subsequent state following this action. The only thing we then still need to clarify is how we compute the weighting coefficient b that is used here. And in our work so far, we've used a very simple formula for this that makes b decay over time, as the given action is sampled more and more. There's another tunable parameter here, beta, which helps us control how quickly MCTS forgets about the initially important novelty and starts focusing on value in the limit instead, which preserves all MCTS convergence guarantees. And that's all the modification we need to turn vanilla MCTS into novelty-enhanced MCTS. Now that I've explained how it works, I'm going to finally tell you if it works in the experimental section. So far, we've compared novelty-enhanced MCTS to regular vanilla MCTS in 4 different board game domains: in Connect 4, Othello, Breakthrough, and Night Through. All MCTS players in our experiments used heuristic state evaluation functions to guide our search and to provide the feature representations that we used for the pseudocount novelty measure we defined on evaluation features. The 3 novelty measures were all tested in the 4 test domains at both 1000 and 5000 MCTS simulations per move for both players, in order to test whether novelty can increase the sample efficiency of the search. The 3 tables of results I'm going to show you will therefore have this shape, and will show you the win rate of novelty-enhanced MCTS versus vanilla MCTS, so that values higher than 50% mean better performance through novelty. The bold font indicates statistically significant improvements. So let's start with the results for the evaluation novelty. We don't need to go through every single figure here, but we can make 4 general observations. First, novelty works better in some test domains than in others. Best in Connect 4, followed by still good results in Breakthrough and Night Through, and no effect of novelty in Othello. Second, the idea of enhancing MCTS exploration with novelty seems to be overall promising. Out of 8 conditions here, for example, 5 were significantly improved by taking novelty into account. And third, novelty seems to be more effective at higher search budgets. The results are overall quite a bit stronger at 5000 than at 1000 simulations. And interestingly, when we compare to the results for the pseudocount novelty based on atomic state features now, as well as the results for the pseudocount novelty based on evaluation features, and we put them all next to each other, we can see that they're all very similar, and our observations apply to all 3 novelty measures. Whether novelty helps or doesn't help, therefore, seems to depend more on the domain or on the evaluation function guiding the search. Maybe on how often the evaluation is misleading, for example, than on the precise novelty measure chosen. This is promising for future research on computationally efficient novelty definitions for online search, which perform well at equal wall clock time as well. So we've arrived at the conclusions and a little outlook on future work. Our preliminary results show that in 3 out of 4 game domains, all tested novelty concepts are successful at improving the performance of MCTS, as a sort of online generalization of uncertainty. There's a lot more future work possible on additional novelty measures, on a wider range of different test domains, and on experiments that take the time overhead of novelty computations into account. In domains where exploration is particularly tricky, we expect that combining multiple novelty measures could be promising, similar to an approach we're presenting at GECCO this year on combining multiple value estimates. In addition, we'd like to examine whether novelty-enhanced MCTS really works best when deceptive or lower quality heuristics are guiding the search. So far, our results don't really point in that direction. And last but not least, future work could also look at novelty-enhanced MCTS guided by neural networks, such as in the AlphaZero or MuZero frameworks, where novelty potentially could improve both planning and learning performance. And that's the end of my talk. For the live audience, we should now have a few minutes for questions, and for everyone else, thank you for listening.